last two talks of today, we have the privilege of having a couple of theorists who have worked quite extensively to understand how light propagates and interacts in low-dimensional systems. So the first speaker is Professor Shanhui Fan from Stanford.
All right. Well, I'd like first to thank the organizer for inviting me to this a really very exciting workshop. I've learned a lot. So here I'd like to talk about some of the basic theory and computational approach for few-photon transport in one-dimensional geometries. In this talk, of course, in this workshop, you of course have heard enormous amount of a wide variety of one-dimensional geometry coupled to quantum emitters, and I here just highlight two of them. That was all very early work. This is, I think, from Jeff Kimball's work, where coupled to a fiber to a cavity, the cavity then coupled to a cesium atom, and the atom itself is a quantum emitter, and the coupling of the photon and the atom here, or the presence of the atom here, influence obviously the transport of light inside the fiber. Here is a work from Misha Lukin's group here at Harvard. What they did is they couple a quantum dot to a silver plasmonic silver nanowire, and in this case, the silver nanowire is a one-dimensional system, and the quantum dot here is a quantum emitter that again can potentially be used to influence few-photon transport inside these one-dimensional system. So as you can hear from this workshop, there are really enormous amount of experimental interest now in thinking about these one-dimensional systems. From a pure intuitive theoretical argument, this is also mentioned in this workshop. Imagine that you have a waveguide and you couple to a two-level system. A long time ago, more than 10 years ago, we calculated this, and what we show is that basically you have a single photon coming in. If you sit in the forward direction, then there are really two pathways the photon to get there. The photon can go directly through, or the photon can excite the atom, and the XN then decay in the forward and backward direction. So in the forward direction, there are really two pathways the photon to get there. And as is typical in these things, when there are two pathways, they will interfere. In this case, they destructively interfere to give rise you a complete reflection of a single photon. So now, what you can do is you inject a two-photon state into the system. And since a two-level system on any given time can only absorb a single photon, these two photons has to compete, let's say, for the seat inside this two-level atom. And consequently, this provides a very natural way to induce photon-photon interaction. So the interesting part, at least at the time when we started looking into this, was the fact that in this case, you have photon-photon interaction coming entirely from spontaneous emission. And there's no cavity that's involved in the system, and it comes about simply from the fact that in nanophotonic waveguide, you can imagine that the two-level system decay predominantly into these waveguide without coupling to the external world. So so what we would like to do here today is to discuss, the waveguide disappeared, to discuss in more detail some of the theoretical model in trying to connect to the experiment, that for example, these kind of experiment, and how we'd like to understand how few-photon state or multi-photon state, when it's propagating inside the waveguide, how that interact with a local quantum system. So here is a brief outline of my talk. It consists of two parts. One of them is a computational part. How do we systematically compute photon-photon interaction in these geometries? And the second part is more of an intuitive set of argument on some of the general aspect of photon-photon interaction in these systems without explicit computation. So let me start with the first part on the computational part. Of course, to do computation, you start by writing down the Hamiltonian. And here we just look at perhaps the simplest Hamiltonian, that we have a waveguide photon. So these are basically propagating mode. And we do the simplest thing here. So we're only having linear dispersion inside the waveguide. And then we couple into a local system here. Maybe I should get the local system here has many degree of quantum variables. In particular, we isolate one of them, and that's called A. And it can be thought of as, for example, the cavity operator or the spin operator if we're trying to couple to two-level system. And the coupling of it is in the rotating wave. So again, we do the simplest kind. We hear a lot of more fancy kind in this workshop already, but here really it's the simplest kind. It's a rotating wave approximation. So in this case, you can destroy one quanta inside the local system and generate a photon, or the external photon in the waveguide can be annihilated and then excite one excitation inside the local system. The local system then itself, of course, has a dynamics that is described by a local Hamiltonian. So it's on one hand, a very generic Hamiltonian because the local system here really can have a wide variety of complexities that we'll be talking about here. On the other hand, compared with, for example, going beyond rotating wave approximation and so on, it's a relatively simple Hamiltonian. Now, the object that we care about then is something called scattering matrix. And a scattering matrix basically says that suppose at time equal to minus infinity in the remote past, you inject two photons and into the system, for example. You can think about n photon as well. And for the sake of argument, you would say that you inject these two photons at pure frequency, so it has k1 and k2. You send into this waveguide, it will propagate and then couple into this local system. Now, the local system has nonlinearity, so these two photons will interact with each other. And as a result of the interaction, you ask, what exactly is the outgoing state? And in particular, you ask, what's the probability of finding the outgoing photon, for example, having frequencies P1 and P2 inside the system? Now, this is a simple example of a two-photon S matrix. But of course, you can straightforwardly generalize this to n-photon S matrix without any difficulty. There are several reasons that one actually are interested in these kind of S matrix formalism. One of them is that this, in many ways, is a somewhat of a theorist view of how an experiment is being done. You send in a few photons, and you look at how the few photons come out. So that's one way of saying it. The other point from a pure theory view is that the S matrix is probably the strongest constraint theoretical object that you can ever find in field theory. So as a result, there are actually a lot of important constraints that you need to build in to construct the correct S matrix. And so as a result, from a theory point of view, being able to compute and figure out general properties of these S matrix can turn out to be quite important. So now, there is actually a very large literature that exists already in computing these kind of few-photon S matrix in one-dimensional geometries. There are probably hundreds of them, so I couldn't list them. What we would like to show, however, here is perhaps one method of doing so that I think really highlights some of the general aspects of the properties of these S matrix. And also, the vast majority of these papers confine themselves in the computation only of one or two photon scattering matrix. And what we like to do is to find a systematic way to look beyond the two photon into the multi-photon regime. So that really motivates some of the computational work that I'm going to talk about here. So what we do here, and that's a program that's been ongoing in my group for the past couple of years, is to use a formalism that actually is very well known in the quantum optics community called input-output formalism. And this is developed by Gardner and Corlett in 1985. It's a very standard approach in quantum optics for treating open quantum systems. And it has been mostly been used to treat the response of the system to coherent or squeeze state input. So as a result, it has been generally formulated as a quantum stochastic method in treating the response of these open quantum systems. What we have done a couple of years ago, on the other hand, is to take the same formalism, basically we copy them, but we adopt it for the computation of S matrix for few-photon Fock state. And here, what we like to show is how to do that systematically for n-photon transport. So as a start of this formalism, so the waveguide itself is described by what's called the input and output operators. And the CK here is the standard operator of the waveguide photon. Now you consider for the input operator, you consider these waveguide photon at a remote path, so at t goes to -infinity. And then you form a linear superposition of all these photons at remote paths into an input quantum field with a time label. And so the time label actually is a convenience here. The important point here is that the input field consists of photons at remote paths. Similarly, the output field is constructed for photon at a remote future. So these are all Heisenberg operators that describe the waveguide system. Knowing this, you can actually make connection to the standard scattering theory formalism to convince yourself that the standard scattering theory S matrix, which talk about m photon at m momenta in and m photon at m momenta out, can actually be written in terms of a Fourier transform of a time domain scattering matrix. And the time domain scattering matrix has a very intuitive form where you essentially inject m photon and then you remove m photons. Now, the somewhat amusing point here is that, of course, you inject these m photons all at remote paths, because these are all Heisenberg operators at t goes to -infinity. But nevertheless, each of these operator has an additional time label that you are going to do Fourier transform for in order to get the S matrix. But it's just but intuitively, I think if you just read naively how this thing look like, it actually makes sense. You inject m photon in, remove m photon out, you get the S matrix out of the system. Right. So our objective here then is to compute, therefore, this particular object, this basically S matrix in time. And now that's the waveguide. The local system itself, without the waveguide, is a purely Hermitian, is described by a purely Hermitian Hamiltonian system. Nothing to be said about it. I just highlight the variable here, A, because that's a variable that's going to be coupled to the waveguide. Now, when you put the waveguide in, then you can actually derive the system in this set of very simple equation, at least on the face of it. In terms of the local system variable, the first term here, the first term here is just the Heisenberg equation of motion of local system. Then you have a exponential decay here that make the system non-Hermitian, and therefore, in fact, the eigenstates of the system are non-orthogonal, as Jeff. Okay, thank you. As Jeff emphasized actually in the morning in one of the comments. And compensating for the exponential decay here is the input quantum field. So that actually recover the usual commutation relation of the local system commutator. And then the output field is then related in two parts. One of them is a direct transmission, so it's an input field by itself, and then the decay of the local system. So it's a local system times a decay constant. So this equation is a purely Heisenberg, is entirely in the Heisenberg picture. So these are operator equation. Once you have nonlinearity here, of course, it becomes highly non-trivial to solve. On the other hand, in form is actually very similar. In fact, it's identical to what's called the classical temporal couple mode theory that people have extensively used to describe nanophotonic geometry. So there is actually a very interesting connection between quantum and classical system in this kind of formalism as well. So the main result of our work is then to start with the this input-output formalism and to show that the m-photon S matrix in time domain can be entirely written in this form. It's a somewhat complicated formula, but essentially what you do is you pick m of those times out of n, and you form a correlation function in terms only of the local variable of the local system, and the rest of it goes to delta function. So to see where this result comes from, now, first of all, one of these terms, for example, you can illustrate this by looking at a 3-photon system, so a 3-photon S matrix. Imagine you're trying to compute 3-photon in, 3-photon out, and the S matrix for that. Then you just need to sum over these terms, and one of the terms that you need to sum over is a term that looks like this, where you have a delta function, and that tell you the first photon basically bypass the local system. Then you have a correlation function, which tell you that the remaining 2 photons couple into the local system, then decay away. So in this case, what you see is that all you need is to compute actually the green function of the local system. And the computation, the S computation of the S matrix then is then reduced to treating this green function of the local system, which at its most fundamental level is just a finite small dimensional problem. So it's something that you can treat either analytically or numerically. So I show you one term of the 3-photon S matrix, and you can write down, at least graphically, all the terms that you have. For example, if you want to have a 3-photon S matrix, it's just these 4 class of terms. One of them is that all 3 photons bypassing the local system, so you get 3 delta function. Then you have 2 of them bypassing, 1 of them go in, so you have 2 of the delta function here. This turned out to be the delta function as well. This one I've shown you, and then the last one, you have all 3 photons couple in and out the local system. Now, the proof of this formula actually turned out to be extremely general. And the only thing that you need to use is a relation called quantum causality. So in input-output formalism, there's a set of commutation relation that Gardner and Corlett has emphasized. And this commutation relation actually tells something very physical. What it says is that your input field, your local variable, has to come from the input field at a time label before that. And so consequently, the local field will commute with input field variable if the time label of the input field is after the local field. And similarly, the output field can only be generated by the local variable here, can only be if t is less than t prime. So in other words, the output field here can only see a local field. The output field here can only come from the local quantum system field if the time is afterwards. And from this quantum causality, you can then derive a set of operator commutation relation. And so which basically tell you this kind of time dependency of the system. Now, this come out of causality, and it actually is generally applicable and is completely independent of the detail of the local Hamiltonian. So with this, you can actually, in a few lines of very simple algebra, decompose the n-photon scattering matrix into the green function of the local system. What you essentially do is you start with the output operator. You use the input-output relation to write it in terms of linear superposition of the input operator and the local field operator. Now then you expand. And as you do that, you get 2 to the n terms. And you apply basically the quantum causality relation. You find yourself that all the terms that contain the input operator actually disappear. Then you do the same thing. You basically expand this guy. And again, you're going to expand it into output and the local operator here. And again, you expand it. And when you do that, what you are going to find is that actually every single term contains the input and output operator. Every one of them is actually eliminated by quantum causality. In other words, quantum causality, you can move them basically to the end of these commutation, of these very complicated product of all the operators. You can move them to the end, and all of them disappear. So as a result, what you end up is just a green function of the local system that you can compute. So I would like to give a very simple example. This turned out to be a chiral example, and I just heard this very exciting talk that Peter just gave about chiral system. You have a waveguide couple, in this case, a ring cavity. So, and the ring cavity support a Kerr nonlinearity. And you can do this computation for this system. For single photon, you just need to calculate a 2-point Green function for the cavity photon operator. And this you can almost argue physically because, well, if you excite a cavity photon at time t prime and then remove it at time later t, then of course this is exponential decay. So expect that the Fourier transform is a Lorentzian. And then if you do the calculation combined with the Dirac pathway, you get a all-pass response. And you basically get a frequency-dependent phase shift in these kind of system, which is what you expect classically. Now you can do a 2-photon calculation. In this case, you just need to compute a time-ordered 4-point Green function, again for the local system. And in this case, depending on the time order, it actually tells you something about 1 or 2 photon excitation. So for example, if the time order is in this order, then you will be creating 2 photons first and then eliminate it afterwards in the cavity. And as a result, that involves 2-photon excitation inside the cavity. On the other hand, if the time label is in this order, then you would put in a cavity, eliminate it, put in a photon, eliminate it, then put in a photon, then eliminate it. And that term there, therefore, involves only 1 photon excitation. So in a single time order product, actually you can see that it connects both to the 2-photon and 1-photon excitation of the system. And the single photon excitation, of course, has a resonant frequency omega c, and the 2-photon excitation has the extra interaction term. So putting this together, then you can write down basically the 2-photon scattering matrix, and it generally has this form. The first line here is the non-interacting part. Basically, each individual photon passes through the cavity, acquire its phase, and then this is uncorrelated process. So when you have 2 photons in, then the total phase is just a product of the 2. And in this process, individual photon energy is conserved. Then you have the correlated part, which only have a single delta function. So the total energy is conserved, but the individual photon energy is not conserved. And the prefactor in front of this delta function here has both a single photon pole that comes of the single photon excitation, as well as a 2-photon pole inside the system. So you can go through this process and go compute 3 photons. Again, you can write down basically a 3-photon correlation function. There are really 3 different kinds of terms involving 3-photon excitations, 2-photon excitations, and 1-photon excitations, and so on. Depending on time order, you then put it in, and then you can go compute the 3-photon S matrix for these kind of systems as well. So what we present here is really a low-dimensional object like this, that if you can compute them, you will be able to compute the n-photon scattering matrix. So that concludes, I guess, the first part of my talk, where I'm trying to argue that to compute photon-photon interaction in these systems, you can reduce them to an object that really has very low dimensionality. In the second part of my talk, I'm going to switch gear a little bit and talk about some of the aspects of these scattering matrix that you can argue without explicit computation, which is somewhat tedious, actually, as you probably will be convinced after hearing me talking for 20 minutes. Now, let me get back to the system that I just shown you, where I have a waveguide side coupled to a Kerr nonlinear cavity and the 2-photon scattering matrix. You can see this 2-photon scattering matrix actually has a fairly interesting form. It has an uncorrelated part where the single photon energy is conserved. Then it has a correlated part where the total energy is conserved, but not the single photon energy. And this, in fact, is a very general result. If you go examine the very long list of papers that I've shown you where people compute two-photon scattering matrix. The exact two-photon scattering matrix always have a formula look like this. That the first part of it is the uncorrelated part where you take the single photon S matrix, multiply together, and in which case you have a conservation of single photon energy. The second part of it look like this, where you only have a single delta function. Then you have a term that has no delta function in front of it. So what you have, therefore, is a conservation of the total energy, but not the conservation of individual photon energy. If you skim through the literature of that very large number of papers, you would never see somebody claim to have calculated a scattering matrix that looks like this, where the correlated part conserves single photon energy as well. In other words, in these processes, the single photon frequency actually is not conserved, and there's always frequency broadening and entanglement. Now the question is why? So in fact, this has something to do with a fairly important result in quantum field theory called cluster decomposition theory. This is very old results. And the cluster decomposition theorem in field theory in essence tells you that the scattering matrix is very strongly constrained. There are additional constraints to time reversal symmetry and energy conservation. In addition to it, if the interaction is local, there are additional constraints of the scattering matrix. Now, the presentation of a cluster decomposition theorem in standard textbook is maybe somewhat murky. So what I like to do here is to give you a much more simplified version, but essentially of the same argument for the system that we're talking about. So let's imagine a system where you have a waveguide and you have a two-level system. You have a pulse that comes in. Now think of a single photon pulse. So as the pulse comes in, you look at the excitation of the atom. Physically, you expect a leading edge where you start to excite the two-level system. Then after the pulse passes through, the excitation is going to decay, and it's going to decay exponentially due to spontaneous emission. So that shouldn't be too surprising. Now, imagine now you think about a two-photon process, but you do it in a very specific kind. You will say, well, let me take a pulse that I just showed you, which has a finite extent in time. I send it into the system. Then I wait a very long time, and I send in a second photon. So that's a two-photon pulse that you can send in the system. Now, in this case, because the interaction will occur only when the system is in the excited state. In other words, it's a local system, so interaction will occur only if both photons are in the local system. And if you take L to go to infinity, then the two photons basically won't be in the local system at the same time. So if you take L go to infinity limit, then the strength of the interaction as characterized by the T matrix operates on this state should decay to 0. And this is actually the argument of the cluster decomposition theorem. So consequently, now this actually constrains the form of the S matrix that you can take. For example, if you write down the additional interaction part in this form, and you go check on how this particular T matrix operates on the two-photon state, is going to change as a function of L. And in a few lines of algebra, you can convince yourself that it doesn't decay to 0. So the result is that this form here actually cannot be created if you have local interaction. So in other words, the constraint here from the cluster decomposition is that the form can only look like this, that have a single delta function here. It cannot have two delta functions inside the system, and so the frequency broadening entanglement is intrinsic to this local system. Using the same argument, one can actually give further constraint on some of the analytic properties of the two-photon scattering matrix. For example, if you take a instant single photon pulse, and you look and excite this two-level atom. Again, you look at this tail. You can see that this tail will decay exponentially, and they're just spontaneous process. Now, as I mentioned, the interaction need to occur when both photons are there. In other words, when the two-level system is in excited state. So consequently, when you apply the T matrix, the interaction part, to this particular two-pulse, two-photon state, you should expect that the result of it should also decay exponentially as controlled by the single photon excitation. So consequently, you can argue that the T matrix actually need to contain a set of all the single photon pole in the system. So as well as potentially a two excitation pole of the localized region, but nothing else. The rest should be an analytic function. So by this two-pulse experiment, a thought experiment, you can actually constrain the analytic property of the entire S matrix. And in particular, the single photon property in terms of a single photon pole play a very prominent role in understanding the photon-photon interaction inside these systems. So coming back, and this is exactly the form that we see in this system that we've been talking about. You have the excitation of the cavity, which gives you single photon pole and two photon pole in the system, a single delta function, and nothing else in the system. And that, remarkably, you don't have to compute. You should have known the result before the calculation is done. Okay. Now, in the last few minutes, I would just briefly comment that knowing this actually gives interesting constraint on the kind of device that you can build. For example, you heard a lot about the interest of constructing a phase gate, where you basically trying to get a device that looks like this. For the two qubits, if both are in one, you have an extra phase. Now, this is an abstract mathematical construction, so you would like to map them into physics. And one of the first questions you may ask yourself is, what does 0 and 1 correspond to? And so there has been, and in the photon case, of course, you think about a photon state, you can think of the 0 and 1 here correspond either to polarization or to frequency. Now, in the case of a polarization, you have already heard this classic paper by Kimball's group, where you can indeed construct a phase gate without any theoretical difficulty. The question, though, is whether you could do a frequency-based phase gate. In other words, you imagine you encode 0 and 1 in terms of the two frequency of a single photon. Now, as we have argued here, once you have the interaction in, this is actually not doable. In other words, if you were having a frequency based phase gate, you will have a T matrix that looks like this being the actual phase factor, but the single photon energy being preserved. This, of course, is something that you should not be able to do, at least in these local systems. Now, I've shown this example a number of times. I showed you the last time. So, for example, naively, you might say, well, a waveguide coupled to a ring cavity give you a pure phase response. So, in fact, you can see that each individual frequency acquire a frequency-dependent phase shift. Okay? And moreover, naively, a Kerr nonlinearity is typically presented as an intensity-dependent phase shift. So naively, you may say, well, now I have two photons and therefore both present, then I can add an extra phase to create for me a frequency-based phase gate. But of course, we've done the calculation. This you won't be able to see, and in fact, the frequency of these photons would not be preserved in these systems. So with that, let me briefly summarize. I hope to provide you a flavor of some of our recent work, both in trying to advance the computation of these M-photon S matrix, as well as trying to understand some of the basic theoretical constraints on these S matrix from general principle. So with that, let me acknowledge my student, in particular, Shanshan Xu, who had done most of the work that I've been talking about here. And thank you for your attention.
Thanks, Shanhui. Are there any questions? Lana?
You pointed out the difference between the frequency domain and polarization and that's but isn't the real difference that in that Dominguez proposal the photons interact individually with the atom and therefore they are never there at the same time and therefore individual photon energy has to be conserved, whereas in your system they interact at the same time and therefore they can be distributed and conserve photon energy?
I think there's that part of it as well. There's that part of the argument as well. Yes.
So it's not, it means that it's not frequency losses polarization, right?
Right. It's really the local interaction aspect that's important. Yes.
So does any of this beautiful structure carry through to cases where you have just a nonlinear medium that's not localized? Just, photons that interact maybe locally or some
So the delayed interaction that we just commented on is one example where you essentially have an infinite one. But without it, what you have is then you are almost forced to think about infinite systems.
Yeah, so once we think about infinite systems,
right.
Does any of this apply or nothing? All of this is out the window, like structure of the...
So what matters is that the interaction is local. So when the cluster decomposition was initially constructed, one is looking at a scattering of point particles, and the scattering will occur only when the particles are very close to each other.
That's still true, but in your case, there was like a special place that actually was...
That's right.
But suppose they can interact anywhere, but they must come together to interact. Like,
right.
Will any of this apply?
I would imagine so, yes.
Chris?
So as far as I understand it, in your model, there was no decoherence in the local system other than, say, a link to the line.
Right.
So in the system that superconducting qubits, we're not
right.
worried about pure dephasing in the
right.
local system. Do you have a sense of how this might, or whether this would change some of these constraints on the Green function?
Certainly, it will go into the Green function, and so if anything, it would largely these all go to the direction of eliminating the interaction, right? The dephasing or the loss, additional loss of it. So we are in many ways looking maybe the constraint in the most ideal case where you have the ideal interaction. Certainly, this interaction effect is not trivial to observe, and many of the dephasing effect will eliminate it.
So there's this formal structure, this scattering matrix has to have.
Mm-hmm.
And if I just take the piece I like,
okay,
and then I calculate something and I get some fidelity for a phase gate,
mm-hmm.
then the question is, okay, the other piece, which is mandated theoretically for consistency,
mm-hmm.
says, well, that's got to be there and it's going to spoil fidelity. And the question is that extra piece, infinitesimally small? What's the ratio of these terms? The one I'd like to have and to make this other than the one I had to have.
Yeah.
Can you twiddle to make that as small as you want?
Well, given that it's a continuum bandwidth without delta function, you would think that if you frequency filter, then you are, as you make the frequency narrower and narrower, you are getting less and less of a slice. So the interaction effect should go down. So I would have argued that almost there's sort of a trade-off between the frequency bandwidth that you care about versus, in this case, a spontaneous emission line with that kind of a ratio will give you some sort of measure of fidelity. In other words, the high...
To know that for real example.
Sorry?
It would be interesting to
right.
know that for real example.
It will be interesting.
99.99
yeah.
Just by filtering out the little bit of
right.
stuff that's in that second term.
Right. I would imagine that as you filter down, the interaction goes down as well. But we need to calculate. We have not done that.
It's actually, I think it's very interesting insight, but somehow it seems to me that maybe it's not quite kind of complete story. Because, for example, in this comparison with one Kimball,
yeah.
it really shows that things like this kind of delay,
mm-hmm.
bandwidth,
yeah.
like memory to bandwidth,
Yeah.
you know, the kind of things really play a role.
So
Also, this thing, what you're doing,
Yeah.
assumes stationary kind of atomic system.
um,
Right? So you don't change properties in time, which is also very much related to this delay bandwidth, right?
right. So this is not a delay bandwidth argument, first of all, because it's just it's a more of a local nature of interaction. Second, I think if you look at, for example, these delay interaction, for example, lambda system, you can write down the, you can show in the two-photon scattering matrix, there is a part that still look like this, and then additional part, they still have the same physical structure. But what's interesting is you can do something in this sector, is how I will argue. But this two-pulse argument should still stays.
But like, for example, if I take lambda system and I
Yeah.
call something and I start changing the property in time.
Oh, that's different. Yeah.
So that's where and I would say that's how you actually kind of can beat this delay bandwidth kind of,
Right.
you know, thing, right? So I mean,
Right.
I think it's kind of very important because, for example, I think I thought that Alexei was asking about rebirth system, which are non-local,
Yeah.
which immediately allow much more kind of possibilities. But I think
Yeah.
in this context, it's this kind of, you know, bandwidth versus memory time. I think this must play a very important role.
That's an interesting point. Certainly, we do not look into these light stopping systems and delay bandwidth that where can vary function time, that kind of system. This is, I think, is very interesting direction. We have not done.
It's also the assumption that basically the Hamiltonian is not changed externally, right?
That's correct. Yeah.
Because that is also that's another thing which is in this one symbol
Okay.
protocol is also
Yeah.
that to change that to
Right.
has to be part of
Yeah.
it, you know?
Yeah. This, in many ways, apply. I'm not making a general claim about every Hamiltonian. I'm not making that claim. I'm making exactly like Misha, what you said, a time-independent Hamiltonian that's local in space that you send in a few photons to scatter against each other. Okay. And not anything beyond. I do not make any claim beyond that point.
Maybe one more question.
So in your first half, right?
Yeah.
You calculate this time correlated, Green's function. So I guess that's just the quantum regression theorem. You need to calculate that.
Say it again. I didn't hear.
You just need to calculate that with the quantum regression theorem, right?
Perhaps. I think what we do, given that